Hello folks and welcome back to my basement. We have just a little bit left on lecture 7 to go through. I'm going to pick up on slide 19 to describe categorical predictors with issues. So up to this point we would have been through the earlier part of this lecture as well as the corresponding example 7, which includes a few demonstrations of how to include predictors that are categorical and interactions between them. So it's up to you whether you do the coding yourself to represent the group contrasts or whether you let the program do some of the work for you. The latter is less typing, but then potentially more complicated in terms of distinguishing marginal from conditional effects. And all of that works just fine, so long as your predictor variables can be fully crossed. So for instance, in looking at, we had an interaction of binary gender with 3-group dementia. There were people in all possible 6 categories. And so you could let the program estimate the interaction terms and do the coding for you as an option. But what if that wasn't the case? What if your design was not fully crossed? And so I want to show you how to use the same concepts of main effects, conditional main effects, and interaction terms, or what look like interaction terms, to address situations in which predictor effects cannot logically apply to all people from your sample. So 2 specific examples I want to show you just within these slides here. The idea of ANOVA with a hole in it, as one of my students once characterized her design, as well as predictors that don't apply or weren't measured for everyone. And I want to show you briefly the logic by which these designs can be analyzed using nested effects. All programs are capable of fitting nested effects, but the logic and the syntax by which they do so differs. And so I have a common language that I'm going to use that should work across programs that uses pseudo-interaction terms, meaning they look like interaction terms, but given the rest of the model, they're not actually interpreted that way. Instead, they will act as switches that allow predictor effects to turn on or off as a function of other predictors in the model. So for instance, first off, the idea of analysis of variance or traditional linear model interactions among categorical predictors works just fine if you have all possible combinations of values observed. So for instance here, if I have a variable characterized by the numbers and I have a different variable that's characterized by the letters, then I have a design that is fully crossed if there are people in each of these possible combinations. And if I were to use traditional analysis of variance software and tell it that this variable characterized by numbers is categorical and that this variable characterized by letters is categorical, it would return to me a marginal main effect of letter, which would be the difference between the A mean and the B mean marginalized across the other variable. It would also give me a marginal main effect for the means of group 1, 2, and 3 marginalized across the letters, and it would give me the 2 degree of freedom interaction term for how the difference between A and B varies as a function of which number, or how the difference between 1, 2, and 3 varies as a function of A and B. So the marginal main effects here I've highlighted aren't really what you want to know, because the whole point of looking at the combinations of these variables is that you would expect the extent to which A and B differ to vary as a function of these numbers or vice versa. Instead, what we really want to focus on are the values in this table and to be able to characterize an interaction term as a different difference. The extent to which, say, the difference between A and B changes as a function of 1 versus 2 versus 3. So if we keep the focus on the specific differences within the table and we express that same sort of design as a linear model, which is what we've been doing, it would look something like this. So we would set up a coding scheme in which one of the cells is denoted as our reference. Let's say for the sake of easiness here that it's A1. So the intercept for the model would take on the mean for the combination A1. We would have a variable for A versus B, And given the interaction terms, B1 would be specific to the 1 group here. Likewise, we would have contrast for A1 versus A2. So 1 versus 2, which is specific to A given the interaction terms, which would give you these differences in the blue. And then the green focuses on the differences of these differences. So for instance, how the pink mean difference would vary in condition 2 versus condition 3, or how these blue differences would vary in the A group versus the B group. So the software will give you any combination that you can ask for. So I have expressed each of these 6 means as a function of this model and described how then each of these specific differences might be created. So the blue terms give you the differences to get to beta 2 and beta 3, give you these. The pink and the green then give you the combination to get over to the difference between A1 to get down to B is beta 1, and then to get over here, we pick up beta 2, and so beta 4 and beta 5 convey the extent to which you would expect different differences as a function of these interaction terms. And so seeing this type of tabular design through this lens of linear models and these incremental differences that get us across each of the cells in the design comes in handy in the instance in which you do not have all of these particular cells observed, or what one of my students once called ANOVA with a hole in it. So this was the situation in which she came to me for help. She had a experimental design where she had a control group and a treatment group, and it was an overlapping cohort design where they were enrolling people each year. And in cohort 1, she had some folks in each group. In cohort 2, she had some folks in each group. And then in cohort 3, something happened. They ran out of money or otherwise problems occurred and they didn't have a control group. And so she did not know how to analyze differences across these groups, given that she couldn't fit 2 main effects and an interaction term with this hole in the design. Never fear, there is always a way to do this. And so this is the coding scheme that I suggested that she adopt. She could make the cohort 3 treatment group the model reference, and so they would be when all of the predictors to be entered are 0, so I've got the intercept here. Then we could have the difference between cohort 3 and cohort 1 as covered by beta 1, and the difference between cohort 3 and beta 2 as covered by beta 2. Then we have interaction terms. So note what is not included here is a main effect of group. This is the T versus C term is not in the model because it can't be observed for this condition. Instead, I have T versus C entered directly into what looks like an interaction term with T1, which is cohort 1, and then another one that's entered here for cohort 2. And so what this is going to then give us, B3 is going to directly test the difference between control and treatment in cohort 1, and B4 is going to directly test the difference between control and treatment in T2. Because there is no main effect of treatment versus control, when it gets multiplied by these dummy codes for whether it's time 1 versus time 2, that's what cohort means in this case, then these act like conditional main effects. So it's not an interaction term, it's a treatment effect specifically for this time, treatment effect specifically for this time. And so this way of carving up the model, you are allowed to use even if you have a fully crossed design. Because what it amounts to here is these 5 possible means are characterized by 5 distinct fixed effects. Therefore, the 5 means are going to be perfectly recreated in the same way that in the previous fully crossed design, we had 6 different means perfectly recreated by 6 different fixed effects. So it's the same logic, just with one left out because you can't possibly observe it. So this idea that you can have certain model effects be observed only for certain kinds of people is the idea of nested effects. So here's another example. Let's say that in the context of predicting adult development and aging, we are interested in predicting differential outcomes for persons as a function of their dementia type, as well as the timing of their dementia, so how long it's been since their diagnosis. But I want to be able to include persons with or without dementia in the model because I'm going to examine other predictor effects simultaneously. So this creates the same sort of logical problem with a hole in it. For people who do not have dementia, they don't have a type and they don't have a timing. So to be able to include those predictors and not have them be kicked out because they're missing for part of the sample, we have to work around that problem. So what I'm going to do is I have a categorical variable here that has dementia type is either none, AD, which stands for Alzheimer's type, or VA, which stands for vascular type. So I can think of dementia presence as a 3-category variable, none, or 2 different kinds if present. And I'm going to recode that information into 2 different variables. So I'm going to have a dementia variable that is called dem yes, that is a 0 for the none group, and a 1 if they're in either type. So dem yes by itself is going to distinguish the presence of any kind of dementia from the absence. Then within the yes group, I am going to distinguish the AD type versus the VA type, so A or V. And note that 0 is given to the none group because it's not applicable. And so by including both of these contrasts, I will be able to distinguish between my 3 groups, but I'm doing so in a slightly unconventional way, given what I need to do with the rest of the model. So I'm distinguishing group 1 from the mean of 2 and 3, and then I am distinguishing via this contrast of A or V, the mean from 2 from the mean from 3. And I'm keeping these minus 0.5 and plus 0.5 so that they're still 1 unit apart, and so the slope makes sense as the difference for a 1 unit change in this predictor. Then I'm creating a timing variable, and doing so by centering it at 5 years. And note this part here, this is the important part. If dem type equals none, I am saying that their timing predictor is 0. So I am inputting data into cases that would otherwise have missing data here because you can't have a dementia diagnosis timing if you don't have dementia. I know that looks crazy, but stay tuned. In just a second, we'll see that these zeros are not going to be treated as actual zeros. In contrast, for these other 2 groups, I am taking whatever time it's been since they were diagnosed and subtracting 5 years so that my reference group is going to be someone who has had this problem known for at least 5 years, for 5 years. So then I would have a model that looks something like this. So I might have other variables that logically apply to all of the people in my analysis. So I might have also control for age, control for gender, control for education, yada, yada, yada. And this is the part of the model that I want to focus on for current purposes to demonstrate the effect of nested predictors. So this subset of the model. So given my variables, I have dem yes, which is the difference between people who do not versus do have dementia. And that's coded 0 if you don't. And then dem A or V is the type, which is coded 0 if you don't. And the people who don't have dementia were given a dem time of 0. So all 3 of those conditions create an intercept that has the definition of somebody who does not have dementia. They don't have a timing because they were given a 0, and the none group is when both of my group contrasts are coded 0 like usual. So if you don't have dementia, your expected value is given by the intercept. Then we go into the effect of dem yes, which is also included in an interaction term, and therefore it is a conditional effect. So this is the simple slope for the difference between persons without dementia or with dementia. So the effect of having any kind of dementia for people who have had it 5 years. So the effect, it's contrasting people who do not have it with people who've had dementia for 5 years, sort of as a subgroup type idea, but we're not categorizing dementia timing. A or V then is among people who've had dementia for 5 years, the difference of the VA group relative to the A group. Then we get into what looks like interaction terms from here. From this perspective, it certainly does, but it's not really an interaction term because there is no main effect of dem time minus 5. There is no main effect because the effect of dementia cannot apply to timing. The effect of dementia timing cannot apply to the none group. They're a constant. So they don't get a main effect in the model. So consequently, the way that we interpret this beta 3 is dem yes acts as a switch. If dem yes is 1, then they have a diagnosis. Then, given that they have a diagnosis, we can adjust their expected outcome by the number of years in which they've been diagnosed, with 5 as the reference. So then this term, beta 3, is the slope for the difference in the outcome per year of dementia only in persons who have dementia. So dem time does not get to have an effect unless we're talking about the yes group. And so that is why it's okay that I have a 0 here for the none group, is because this variable is never going to be used in creating an expected outcome for the none group. It's not in the model. This variable only has an effect in the model for the AD or VA groups because dem time is never entered all by itself. It's only entered as an interaction of dem yes. And so another way of saying that is that dem time is a nested effect. It is nested within this dem yes group specifically and only. So the effect of timing then is for anybody who has a diagnosis, and then the remaining term beta 4 here serves to differentiate the effect of timing between A and V. And so that is an interaction term because dem A or V is included as a main effect. And so relative to that, we can think of this as the difference in the timing slope between persons with type equals AD versus type equals BA. So it gets tricky to interpret these things, but just know that what you put in the model is under your control. So if you have a predictor that is either not measured for everybody or not applicable to everybody, the way to put its effect in the model is as a nested effect, where it's attached to a switch-like variable that turns on when it should be applied to someone's score versus when it should not. And the provision of a value for all predictors is necessary in order to keep those cases from being kicked out of the model. But the value that's provided really doesn't matter. I'm putting 0 here so that then it makes it easier in terms of the coding to think about what should happen. Even if you forget the switch, because everybody has a 0, their score won't change. But the specification here with the dem yes switch makes it more explicit what the model says is going to happen. This effect of dem time only kicks in for those who have dementia. Pretty cool. So nested effects are the idea that a certain predictor effect only applies to some people in the model. So they're main effects that apply selectively. There are lots of different cases of this. One example is the idea of taking what would be a 0 inflated type of outcome, but treating it that way as a predictor instead. So I refer to these as if and how much types of models, but fitted to a predictor. So you can think of this also as a semi-continuous or semi-quantitative predictor. Here are a couple examples. For instance, in chapter 12 of my book, I describe an analysis that features a group of younger adults who are mostly homogeneous in age. They are a college sample. And then a group of older adults that have a lot more variability in their age, 20 years worth or so. And so I fit a model that looks at the difference of how older differs from younger and treating younger as one group that has just one value. But within the older group, I fit a nested effect of age. So I have an age slope for how old you are, but only if you're in the older group. Alternatively, it's common to have predictors that measure the presence and severity of a problem. So drug abuse, history of physical violence or physical abuse, that kind of thing. So if you have people in your sample who are not, do not have a history of abuse, then they're going to have a 0 on any variable that indexes severity. So one way to address this type of heterogeneity is to have a variable that captures, did you get a 0 or anything above a 0? Anything above a 0, then you're in the at least somewhat abused category. So you could have a mean difference for abused versus not abused, and then within the abused persons, have a nested effect for severity. And so then you can distinguish amongst levels of abuse in addition to presence or absence of abuse as a predictor. As another example, missing data or otherwise some sort of complete data. So if you have a question that some people didn't answer, the fact that they didn't answer it may actually be informative for predicting their outcome. So you might include whether or not someone gave an answer to a question as a predictor, and then if they answered it, what was their answer? So that's another instance of a nested effect within the group that answered the question. Obviously, you don't know what they would have said if they didn't answer, but at least then you can keep those cases in the analysis and look at mean differences in your outcome as a function of who chose to answer, and then further within that group what their answer actually was. And this use of nested effects is also used in characterizing multivariate models. And so if you're going to predict certain effects for one DV and certain effects for another DV, where DV means an outcome, then nested effects allow you to turn effects and predictors on or off across different outcomes in a model, as well as to constrain them to be equal across outcomes if you so choose. And so the latter, multivariate examples, are featured in my generalized linear modeling class to be coming back, I think spring 2022, most likely. So if you're not able to wait until then, of course, this class is on the YouTube as well. So that's it. See you next spring.